Next up on our discussion of vibratory motion, we look at a few examples. So, consider the following example. A 0.68 kilogram block is attached to a horizontal spring as shown in the figure. It is pulled 11 centimeters and then released. The spring has a spring constant of 65 Newton per meter. Ignoring friction, determine the following: the frequency and period of the resulting motion, the amplitude of the oscillation, the maximum speed that the object can reach in the oscillation, and write down the acceleration function. M is equal to 0.68 kilograms. Let K be 65 Newton per meter, and let X initial X naught be 11 centimeters. Spring is used for the vibratory motion. This is spring motion. And for spring motion, the angular frequency is equal to square root of K over M. Knowing mass and spring constant, we are able to calculate the angular frequency, 9.77692311 radian per second. Knowing the angular frequency, we are then able to determine the period of the vibratory motion. And knowing the period of the vibratory motion, we are then able to calculate the frequency of the vibratory motion, as frequency is just the inverse of the period. So we get period 0.643 seconds and frequency 1.556 Hertz. Using the initial position, X initial is equal to 11 centimeters, and at that position the object has just been released, so V initial is 0. And using the conservation of energy equation, we are able to determine the amplitude of the vibratory motion, 0.11 meters. And knowing the amplitude, we are able to determine the maximum speed of the object. You will recall that Vmax is equal to A omega, which gives us 1.075 meters per second. As for the acceleration function, we know that the general equation for acceleration function is A is equal to negative amplitude omega squared cosine of omega t plus phi. Again, we use the initial position. X initial is equal to 11 centimeters. Initial time is 0, but this time we use the position function. And we get the phase constant to be 0. Now, we are able to write down the acceleration function, knowing the amplitude, angular frequency, and phase constant. Next, we have the following problem. At t is equal to 0, the position of a particle in a linear oscillator is x is equal to negative 8.50 centimeters. Likewise, at t is equal to 0, the velocity is negative 0.920 meters per second, and the acceleration is positive 47.0 meters per second squared. Determine the phase constant and the amplitude of the oscillation. So here we have the values of x, v, and a at t is equal to 0. First, we look at the position function. X is equal to a cosine of omega t plus phi. And we put in the value of x and t into the equation as shown. Then we do the acceleration function. A is equal to negative a omega squared cosine of omega t plus phi, and we put in the value of a and t. Dividing the equation of x with or by the equation of a, we see that the only unknown left is angular frequency. We calculate omega to be 23.51470,128 radians per second. We do the same thing with the position function and velocity function, and we are able to get the following equation. Tangent of phi is equal to negative 0.4602877699. Getting the inverse tangent gives us the phase constant. Phi is equal to negative 0.431376271 radians. Note, however, if we use this value of the phase constant to determine the amplitude, we get a negative answer. But amplitude must always be positive, so we need to make a correction to our value of the phase constant. If we get the supplementary angle to the phase constant that we calculated, we get 2.71021642.7 radians. The tangent function of this supplementary angle will also give us negative 0.46028776999. That means the supplementary angle is also valid as a value for the phase constant. If we then use that supplementary angle value, we are able to get the value of the amplitude 0.094 meters. And with that, we are done with the topic of vibratory motion. Thank you for watching.